Welcome to UGC's ePathshala lecture series on computer science. The subject is about Introduction to Visualization and the paper is on visualization techniques. Module 35, this is about visualization of spatial data types. So in this module, we are going to learn about the concepts of spatial data, and we are also going to learn the characteristics of the various spatial data. We will also come to know about what are the various spatial data types and how these spatial data are being represented using various representation techniques. And finally, we are going to have a look at various examples in spatial data visualization. So now let us start with what spatial data is. Spatial data is the data or information that identifies the geographic location of features and boundaries on Earth, such as natural or constructed features, which may be oceans or any other kind of such kind of data. This spatial data is usually stored in the coordinate form and topological form, and is the data that can also be easily mapped. So there are various characteristics of this kind of spatial data. These mappable characteristics are the location of the data, which can be represented in the coordinate system. The next one is a size that is associated with the data, which is calculated by the amount of the data and which is also represented in the form of length, area or perimeter of the data. The shape as such is defined as a shape of the feature, which is actually represented as a point, line or area. The data, this kind of spatial data can be a discrete data or it can be in a continuous form also. And there are various types of spatial relationships that are associated with this kind of spatial data. If we look at the nature of this kind of spatial data, they are usually spatially referenced data, which are also called as georeferenced data. The attribute data is associated with the location. Example of such kind of data are related to spatial objects. So these kind of data can be represented in the form of points. So points usually have x and y coordinates associated with them. Using these points, it is possible for us to plot the data such as such as cities, stores, crimes or accidents. The next representation form is a line form. So these line forms are represented in the form of arcs from one source node to the destination node. So example for this kind of representation techniques are the road network or the transmission lines, which can be represented in the form of arcs or lines. The next kind of representation is a polygon kind of representation, which are a series of connected arcs. Using these polygons, it is possible for us to represent the provinces or cities or some kind of census tracts. So first let us have a look at this point spatial data type. So usually a point is called as a zero-dimensional object and has only the property of location, that is x, y. The points can be used to model features such as wells, buildings, people, power, pole, sample location, etc. The other name for a point are vertex or node. So this is an example point spatial data. So if you look at it here, there are various points which are being plotted on the screen, and the other representation is these points are being plotted on a grid or in a matrix form. The next one is a line spatial data. A line is usually called as a one-dimensional object that has the property of length. The lines can be used to represent the roads, streams or falls, boundaries, contacts, etc. Lines are also called as edges or links or chains or arc. In an arc information coverage, an arc starts with a node, has 0 or more vertices and ends with a particular node. So this is an example of the line spatial data. So here we can see the continuous line which flows from one source node to the destination node. So here there are two lines that are being represented. Similarly, the same line is being represented in the form of a grid or in a matrix format. The next kind of spatial data is a polygon spatial data. A polygon is usually called as a two-dimensional object with the properties of area and perimeter associated with it. A polygon can be used to represent a city or some kind of geologic formations or lakes, rivers, etc. The other names that are given for the polygons are faces and zone of the polygon. So, this is an example polygon representation. So, here we can see a polygon which is being defined by a closed set of edges. So, similarly here also the same polygon is being defined by a closed set of edges, and which is, but here it is represented in the form of a matrix or in the form of a grid. So, there are basically three classes of spatial data type as such. One is the geostatistical data, which are represented as points as sample locations. Here there is a continuous variation over the space as such. The other one is the lattice or the regional data, which are represented by polygons or points or centroids. Here the variation is a discrete variation over space, and the observations are associated with the regular or irregular aerial units as such. The other class of spatial data is a point pattern, which is a set of points on a map which represents occurrence of events at locations in spaces. The observation of the variable are made at a particular location x. The assumption that the spatial arrangement is directly related to the interaction between the units of observation. So, here we can see that from polygon to points, the US states are represented to the centroids, and from points to there is another representation from points to polygon. The first one is polygon to points, and the second one is points to polygon kind of representation. So, if you look at this geostatistical data, this geostatistical data or the geospatial data has attributes associated with them and also has a metadata associated with it. So, this is actually a spatial process wherein the indexed set is a fixed subset of R power D, which is going to be a continuous data set. If you look at the data as such, they form the sample points from underlying continuous surface. For example, mining, air quality, house sales prices, etc. So, they are being modeled using various modeling techniques. One such technique is a variogram modeling technique. Here, the objective is to model the continuous variation across the space. The variogram represents or estimates how the spatial dependence varies with respect to the distance, and it also models the distance decay as such. There is another one modeling technique which is called as a Kriging modeling technique, wherein this kind of modeling technique is useful for representing the optimal spatial prediction as such. So, this is an example variogram modeling which is being taken from the Wikipedia. Here actually it has 5 types of we can see that there are 5 types of variogram curves. At the left, the variogram curves depends on the distance between basically 2 different points, and at the right, the corresponding simulated fields in space are constrained by these kind of variograms. So, this is a left representation and this is a right representation which is being modeled in the form of a variogram. The next one is a Kriging modeling technique. This is also another example which has been taken from the Wikipedia. This is an example of a one-dimensional data interpolation which is represented by the Kriging technique with confidence intervals. The squares indicate the location of the data. The square here indicates the location of the data. The Kriging interpolation is shown in the form of red color, which runs along the means of the normally distributed confidence intervals, which is being shown in the form of gray. Nevertheless, the dashed curve also shows a spline that, while smooth, nevertheless departs significantly from the expected intermediate values given by these kind of means. So, we can see that the variation is very less while comparing this red color and the dashed line. This red color indicates the Kriging interpolation model. The next one is a point pattern. In a point pattern, the spatial process as such is that the index set D is represented as a point process where S is random and the data are being mapped as patterns. Examples of these kind of point patterns are locations of diseases, gang shootings, etc. So, here the most important question is that the interest is on focusing on detecting the absence of the spatial randomness, which is also called as a cluster statistics. And there is another one interesting point to note here, which is actually the difference between the clustered points versus the dispersed points. So, if we look at this kind of point pattern analysis, the objective of these kind of point pattern analysis is to assess the spatial randomness of the data set. The interest lies in the location itself, which represents the complete spatial randomness, and this also represents the clustering as well as the dispersion of the points as such. It is basically based on the distance based statistics, wherein we try to calculate the nearest neighbors, and we also look in for some kind of events which occur within a given radius pattern. So, this is one point pattern analysis example which shows some kind of homicides that has occurred in the year 1994 in the area of Pittsburgh. This is actually showing the difference between the gang related homicides and the non-gang related homicides, which are being overlapped and are shown as the gang related is shown in the form of blue color points and the non-gang related are shown in the form of brown color points. So, we can using this kind of point pattern analysis, it is possible for us to understand how the points are being dispersed within this particular radius and how these two ellipses overlap with each other and where are the locations where exactly the point clusters are being formed. All these can be analyzed using this point pattern example. The next type is the lattice or regional data. Here the spatial process is about the index set D, which is a fixed collection of countably many points in the space R power D. This is actually a finite discrete spatial unit as such. The data here is going to be either fixed points or discrete locations or regions. Examples for this kind of regional data are country tax rates, state unemployment, etc. Some of the research questions related to this kind of lattice or regional data set is the interest focuses on some kind of statistical inference mechanism, and we also look at some kind of estimation or specification test as such. So, if we look at these kind of spatial data types, there are two formats and they are very different from each other, yet they try to contrast and complement one another when used appropriately for the final output. So, in GIS, that is the Geographical Information System, there are basically two basic spatial data types which are represented as the raster data type and the vector data type. So, if we look at these two types of spatial data types, here there is a raster representation and this is a raster representation of the data, this is a vector representation of the data, this is a real world data as such. So, if we look at these kind of visualization of this kind of spatial data as such, here is a comparison chart which shows the comparison of the vector data as well as the raster data as well as the vector data as such. So, here the left hand side shows the raster data and the right hand side shows the vector data representation. In raster data, we can find that the data points are represented inside grids or represented inside a matrix format. So, here these points are being represented as either raster data or as vector data. This is the line which is being represented as a raster data and the vector data, and this is a region which is being represented as the raster data as well as the vector data, and the data set that is in between shows a real data set as such, and these can be visualized as shown here on the right hand side. So here we can see that there are customers which are represented as brown color dots, streets which are shown as green lines, and then we have parcels which are being delivered to certain locations which are also represented using some particular color method. So here it also shows the elevation and the land usage, where the bottommost is the real world data as such. So if we look at the vector and the raster model, we can see that the vector model, it is going to be very smooth in nature, whereas in the case of raster data model, the data set, the data that is being represented is not represented in a smooth fashion. So some of the characteristics of this kind of vector data is, the vector data provides a way to represent the real world features within the GIS environment, that is a Geographical Information System environment. A vector feature has its shape represented using a geometry. This geometry is made up of one or more interconnected vertices as such. A vertex describes a position in the space using the x, y, and optionally the z axis also. In the vector data model, features on the earth are represented in the form of points, lines or routers, polygons or regions are represented in the form of tints, which are actually triangulated irregular networks. So here you can see that the forest, river and the grassland is being represented using the vector format. So how it is being represented, we can see how the forest, river and the grassland are being represented. So here this is a grassland representation, this is a tree representation, this is a forest representation of a particular area. This is a vector data representation. Some of the advantages of vector data are, they accurately represents the true shape and size of the data set, and they also represent non-continuous data, for example rivers, political boundaries, road lines, etc. Vectors can also store information about the topology. A vector data model uses points that are stored by the real coordinates and so requires a precise coordinate system as such. The geographic coordinate system is actually the latitude or the longitude. In the case of Cartesian coordinate system, we call it as a x and y coordinate system. Some of the disadvantages of this kind of vector data is that the location of each vertex needs to be stored in an explicit way. The vector data has to be converted into a topological structure as such. And these kind of vector data processing is highly processing intensive, and it usually requires some kind of extensive data cleaning as such. Updating or editing of this kind of vector data requires rebuilding of the topology. So these are certain disadvantages associated with the vector data. The next one is a raster data. In the case of raster data, it is a cell-based data which represents which are like the aerial imagery and digital elevation models. The raster data is characterized by pixel values. A raster file is a giant table where each pixel is assigned a specific value from 0 to 255. The meaning behind these values is specified by the user, and they can represent the elevation, temperature, hydrology, etc. of a particular location as such. So this is a raster data representation. So if you look at the raster data model, we can see how it is being mapped. The raster data file, which has got n rows and m columns, which is referenced by x, y location, is mapped on to or georeferenced to the Earth's surface with respect to the x, y location. There are various types of raster data. This is a discrete raster which represents the usage of land. This is a continuous raster data type. So if you look at the continuous raster data image, it looks like this. And if you look at the discrete raster data, which is going to represent the rows, we can see the rows are being represented as lines. So as such, a raster is the best way to store continuously changing values such as some kind of elevation. The analysis are faster and more flexible than vectors for many kind of applications. Some analysis are only possible using these kind of raster data. So here we can see how the winds are being represented as raster data. We have discrete raster as well as continuous raster as such. If you look at this discrete raster, it is relatively few possible values to repeat themselves in adjacent set. For example, the land use, soil types, etc. are represented as discrete raster. So here we can see how this particular data is being mapped down to the discrete raster, which is shown in the right hand side. Examples, some of the other examples of discrete raster are mapping the values onto a table. So here we can see that there are various values. As I said earlier, that these kind of raster data actually are supposed to be represented by individual pixel values as such. So in the table, they represent the value of each and every pixel and the count of each and every pixel data as such. So here if you see this kind of light color data set which has got a value of 1, there are 12 counts, 12 such data as such. Similarly, purple color square which has got a value of 2, the count is about 8 as such. So it goes on like this. So here each raster data set must have some name to distinguish it from other raster data sets as such in a database. All access to the raster data set is performed through its name, which must be used consistently in all other kind of representations and expressions. So here we can see that the name actually follows the value, count, as well as the type, the canopy, and everything has got its own name associated with it, which are being linked only with respect to their names as such. So this is some kind of discrete raster representation. This is an example of a continuous raster representation technique where the data is going to be continuous in nature. So this represents some kind of miles or kilometers, which are by the distances are represented using various colors, the hues, colors and hues. So we can also look at the direction here which is being represented here, and this shows an example of a continuous raster data set that is being visualized as such. So these are some kind of raster analysis function. The density function which can be analyzed as such using this kind of maps, the distance function which can be analyzed using these kind of maps, the interpolation function which is being applied over this, which gives a display of this type. The least cost path method is being applied, which shows a visualization of this method. This one is a viewshed method and the other one is a buffers. So these are various raster analysis functions, examples of raster analysis functions as such. So you have something called as a raster calculator, which does the cell by cell evaluation of some kind of mathematical function. So if you look at this example, it says that the precipitation minus loss gives a runoff. So if you look at the various layer, this is a precipitation layer, this is a loss layer, and the bottom one is a runoff layer. So if you take each and every cell, this cell, the left side most cell, which has got a value of 5 for precipitation and 3 for losses, if you subtract these two values, you get the runoff value, which is represented as 2. Similarly, for all the cells in the grid, if you minus these values, the precipitation values, the losses value from the precipitation value, you get the runoff value, which is being represented or calculated, and this is also called as a raster calculator, which does a cell by cell evaluation of mathematical functions. So here in this example, we have shown the raster as well as the vector data models. So the middle one is a real world data set. this kind of real world data set are supposed to be visualized as raster data as well as vector data model. If you look at the raster data representation, B is represented for the blue color, G represents the green color, and BK represents the house which is being represented here. Here as such, if you look at this vector space, which in the raster representation, we can see that every data is being represented in the form of a pixel value and is being shown in the form of a matrix as such. In the vector representation techniques, if you see, you have the x-axis and the y-axis, and the data set is represented using this x comma y plot. So you have the river plot, you have the trees that are being plotted in their particular location, and the house that is being plotted in the x comma y location as such. So both these data set show or visualize the entire real world as such using two sets of data models. So if you do a comparison between the raster and the vector data type, the data collection has to be rapid in the case of raster data, and vector the data collection is going to be very slow. The data volume in the case of raster is large, whereas in the case of vector data it is small. The graphic treatment in the case of raster data is average, in the case of vector data it is good as such. The data structure in the case of raster data is simple, and vector data it is going to be complex. Geometrical accuracy is going to be low in the case of raster data and high in the case of vector data. Analysis is poor for raster and good for vector. Area analysis is good for raster, whereas in vector it is average, and the generalization of raster data is very simple, whereas in vector data it is a more complex generalization. If you look at the impact of resolution on the display, this is a representation of the raster data as such. We can see the storage space increases by the square of the resolution, and by resolution this kind of raster data representation techniques gets more jaggy in nature, whereas this vector data representation technique, it portrays large areas at high precision and is very clear as such. So it is also possible for us to convert the vector to raster data, and this kind of conversion is also very simple. So you have the vector data that is being represented. Finally, you draw a 10 cross 10, or based on the size of your vector data set, you can draw a square matrix, and you can you can number the cells, and based on the cell number you can convert the vector data to a raster data easily. There are various GIS data formats or file formats as such. The vector data are represented as shape files, coverages, and are also represented as triangulated irregular networks, whereas raster data is represented in the form of grid files and image files. If you look at the shape files, there are no topological information. The advantages are no overhead to process the topology as such. The disadvantages are polygons are double digitized, and there are no topographic data checking, and at least there are 3 different types of files as such. If you look at the coverage files, you have the original ARC information format, and you have the directory with several files. The database files are also stored in the information directory, and it uses ARC node topology, which has got containment, connectivity, and adjacency. The next one is a triangulated irregular network, which is also called as a TIN, which is a data model that is used to represent 3-dimensional objects. So in this case, you can use the x, y, and the z values also is included to represent the points as such. Using methods of computational geometry, the points are connected into what is called as triangulation, forming a network of triangles. The lines of the triangles are called the edges, and the interior area is called as a face or the facet. So this is an example of a triangulated irregular network. So these are the various components of a triangulated irregular network: nodes, edges, triangles, hull, and the topology. Grid also has got its own properties. Each grid cell holds one value, even if it is going to be an empty cell. A cell can hold an index value standing for a particular attribute. The cell resolution is given as its size on the ground. Point and lines move to the center of the cell. Minimum line width is 1 cell, and the raster are easy to read out and write and easy to draw on the screen. So a grid actually defines a geographical space as a matrix of identically sized square cells. Each cell holds a numeric value which measures a geographical attribute, for example like some elevation value for that unit of space. So if you look at the grid data structure, it is defined by the extent, spacing, and there are no data value information. There are number of rows and number of columns. You have cell sizes, you have top, left, bottom and right coordinates, and there are grid values, real and integer. So there are various effects of changing resolutions. You have numerical representation of spatial surface. These are various examples of spatial data visualization. This is a GeoCanvas. This is SynGILF X, which also shows an interactive data visualization in the form of spatial visualization. This is combining the hue, saturation and brightness to visualize different features of a plan as such. So to summarize, we have looked at what a spatial data type is, what are the different natures of this kind of spatial data type or the characteristics of spatial data type, what are the different classes of spatial data, how these kind of spatial data are being represented using various representation techniques, and we have also at the end we have also looked at certain examples of spatial data visualization. Thank you.